After watching this video lecture series, students will be able to understand how spectroscopy is used to study matter and be able to utilize Beer's law to calculate concentrations of unknown samples. Spectroscopy is the use of electromagnetic radiation or light to study matter. There are many types of spectroscopy that take advantage of light properties. In this lecture, though, we're going to be focusing on spectroscopy associated with the visible spectrum. Now, the two types of instrumentation that are commonly used to analyze matter with respect to visible light are spectrophotometers and colorimeters. Okay, and spectrophotometers and colorimeters work in the same basic fashion. However, a spectrophotometer is going to have more wavelengths of light accessible to it than a colorimeter. So basically, a colorimeter can kind of be looked at as a simplified version of a spectrophotometer. So how both of these instruments work is that we initially have a light source. That light source typically is going to have, some wavelengths able to be provided. Okay, so that light source has an incident light that it shines into a monochromator, which basically isolates an individual wavelength from that visible spectrum. That individual wavelength is then shined through a sample. And as that light shines into the sample, some of those photons of a light will be absorbed by the sample that is, or by the molecules that are present in the sample. And then some of those photons will pass through. The light that is passed through is then taken in by a detector, and additional instrumentation or a computer will give you an absorbance spectra. So before we go ahead and talk about absorbance spectra, we need to talk about a couple of other features from this experiment. Okay, so what we notice here, guys, is that you have I naught and I. Okay, the I values are representing the intensity of light associated with the light before it passes through the sample and the intensity of light after it passes through the sample. So the ratio between I and I naught is going to equal transmittance. Now, we know that transmittance is going to be related to the ratio between the light after it passes through the sample and the intensity of the light before it passes through the sample. So, of course, we would expect that if some of the light passes through the sample, that some of it's going to be absorbed by that sample. So we expect our I value to be smaller than our I naught. Okay, now transmittance basically tells you how much light is passing through the sample. Okay, and so if we were to go ahead and multiply the transmittance by 100, okay, we would end up with our percent T, or percent transmittance. Okay, so if we take this ratio and multiply by 100, we'll get our percent transmittance. Now, if we go ahead and we look at the relationship between our percent transmittance and our concentration of our sample, okay, we're going to see a graph or graphical data that kind of looks like this. Okay, and so what we see here, what we can determine here, is that as our concentration is increasing, our percent transmittance is decreasing, which makes sense because as we pass the incident light through the sample, the more concentrated it is, the more molecules will be present to absorb that light, so the less light that will pass through and reach the detector. Now, this is not a linear relationship, so there's obviously a little bit less usefulness in analyzing this data. However, we can relate transmittance to our absorbance. So absorbance is going to equal the negative log of our transmittance. Okay, and if we go ahead and we graph the absorbance versus our concentration, okay, so absorbance versus our concentration, we're going to end up with a linear relationship. Okay, and a linear relationship is going to be able to give us a lot more information about our particular solution. Now, in that same sense that we looked at how concentration and percent transmittance are related, the relationship between concentration and absorbance is directly related, right? Okay, so as concentration increases, your absorbance increases, which is a much more intuitive way to approach the analysis of the data. So why is information like this useful? Okay, well, let's say that I basically create a absorbance spectra with a series of known concentrations. What I can find out, or from that linear relationship between absorbance and concentration, I can determine the concentration of an unknown through analysis of its absorbance value. Okay, so I can basically set up an experiment where I take concentrations of known samples, okay, and basically record their absorbance values in the spectrophotometer or the colorimeter, and I can graph their absorbance versus their concentration. I can then do a linear regression, establish the equation associated with that line, and I can then take an unknown sample and find out its concentration based on the absorbance values I obtain from the spectrophotometer or the colorimeter. So now we're going to take advantage of an equation called Beer's law, which takes advantage of the relationship between, or that direct relationship between concentration and absorbance. Okay, so some variables we need to look at. Okay, C stands for concentration in moles per liter. Okay, your L is your path length of your cuvette. So basically the distance between the edges of the cuvette, which is usually 1 centimeter. And then your molar absorptivity, okay, which is a constant with units of liters per mole times centimeter. Okay. And basically, the direct relationship that we see here, we can use our equation, our y equals mx plus b, from the linear regression that we get here, okay, to relate directly to Beer's law. So we know that if we have an absorbance equal to 0, we know that the y-intercept is going to be 0. So in that context, the b portion, or the intercept portion, is going to be 0. So we can exclude it. So the y equals mx. X is going to correspond to your concentration. Okay, and m is going to correspond to the product of your molar absorptivity and your path length. Okay, and so we can get the data associated with Beer's law from the linear regression of the known concentration values samples. Go ahead and look at an example problem. So the concentration of a sample of aqueous calcium chloride is 10 molar. The absorbance is found for the sample to be 0.209 when this solution is placed in a 1 centimeter cuvette and analyzed with a light having a wavelength of 258 nanometers. So they want us to calculate the molar absorptivity of this sample. So we're going to go ahead and be using Beer's law. So absorbance is going to be equal to the molar absorptivity times the path length times our concentration. Okay, so we've been given our absorption value, our path length, and our concentration. So we're going to solve for epsilon, which is going to be our molar absorptivity value. Okay, so if we go ahead and manipulate this equation, absorbance divided by path length times concentration is going to give us our molar absorptivity value. And if we go ahead and plug these values in that they've given us and do our math, we're going to end up with the following answer, which is going to be 0.0209 liters per mole times centimeters as our molar absorptivity value. Okay, so we've gone ahead and solved this first problem. Okay, so now that we have found out our molar absorptivity value, they want us to figure out what the absorbance value will be if the solution has a concentration of 5 molar. Okay, so again, we're going to be using Beer's law. Okay, and in this sense, or in this case, we know our molar absorptivity, our path length, and of course our concentration. So we're going to go ahead and plug each of those in. Okay, and since we've now plugged those all in, we multiply them all together. That gives us 0.1045 as our absorption value for that concentration. So if we go ahead and we compare the absorbance value for the 5 molar solution and the absorbance value for the 10 molar solution, notice that the absorbance value for the 5 molar solution is going to be lower than that for the 10 molar solution. And this is because the amount of calcium chloride in the 10 molar solution is going to be higher. So there are more molecules to be absorbing the photons of light coming from the incident light that we're shining on the sample. Okay, so if it's going to absorb more of it because there is more of it there, obviously we're going to end up with a higher absorbance value than the sample that has less calcium chloride present.